Bonding Performance by Jasmine Kong and Erica Bartley. Period 7, Miss Cassans. First we made the aluminum boats. Our next step was to light the candle. We used a wooden stick to light the Bunsen burner. Our next step was to watch the substances and record them in the order that they melted. Paraffin wax was the first to melt. The water closely followed. Next, the sucrose melted. The other substances did not melt. We concluded that in terms of relative melting points, paraffin wax had the lowest, while potassium iodine had the highest of them all. We found zinc to be the only conductor in the solid phase. Our next step was to add deionized water to each of the substances. Potassium iodine, sucrose, and sodium chloride were the only soluble substances. We found the paraffin wax and zinc to be the only non-conductors. The results of these experiments told us that zinc is a metallic substance, paraffin wax and sucrose are covalent compounds, and that sodium chloride and potassium iodine are ionic substances. The substances can be divided into 3 groups according to their solubility, conductivity, and relative melting points. Group A consists of only zinc due to its conductivity in both the solid phase and while being submerged in water. It is insoluble and has a somewhat high melting point. Group B includes paraffin wax and sucrose, which have similar properties. They are non-conductive in water and usually have low melting points. Lastly, Group C has sodium chloride and potassium iodine. They both have very high melting points, are soluble in water, and only conduct electricity in the liquid phase. We can conclude that Group A has metallic substances, Group B has covalent substances, and that Group C has ionic substances. Paraffin wax and zinc were the only substances not soluble in water. If there's an unknown substance that has a metal and a non-metal in its formula, it should dissolve in water because if it has a large electronegativity difference, it is polar. The opposite charges on the non-metal are attracted by the partially negative hydrogen particles and the partially positive oxygen. Opposites attract, so water molecules will be pulling separate ions from the crystals. We found that paraffin wax and sucrose were not conductive in the solid phase or in water. Sodium chloride and potassium iodine were not conductive in the solid phase, but both were conductive in water. Zinc was conductive in both the solid phase and in water. Ionic substances have very high melting points, strong bonds, and are conductive in liquid phase. Metallic substances have moderately high melting points. They are insoluble and conductive in both the solid phase and submerged in water. Covalent substances have low melting points, are usually insoluble, have weak bonds, and are non-conductive in all phases of matter. In this experiment, we recorded how many drops of both ethanol and water could fit on a penny. It all depends on a substance's molecular polarity, intermolecular forces, and surface tension to differentiate the quantity of drops a penny could hold. If a molecular substance is more polar, it will have a stronger intermolecular forces, hydrogen bonding or dipole-dipole, than a less polar substance, which will tend to have van der Waals forces or temporary attractions due to the piling up of electrons. The intermolecular forces will then affect surface tension. The stronger the forces, the higher the surface tension, which is liquid's resistance to compression. Therefore, with stronger bonds, objects can be resisted, including water piling up on itself, until the weight of the resisted objects cannot be held back anymore by the bonds. We found that the stronger the intermolecular forces are, the higher the surface tension is. In trial 1, the penny held 24 drops of water and 26 drops of ethanol. In trial 2, the penny held 23 drops of water and 17 drops of ethanol. This station was where we assembled molecular models of each substance. By doing this, we were able to see the molecular shape of each of them. There are a different amount of holes in each atom because each atom needs a different amount of electrons to be stable. There are possible areas where electrons can be shared between another atom because of this. The amount of electrons an atom needs to be stable determines the amount of holes it has. Since the hydrogen-oxygen molecules both had no electronegativity differences and were symmetrical, we classified them as nonpolar. We also classified methane and carbon disulfide as nonpolar because they had very small differences in electronegativity, equal charge distribution, and were symmetrical. We classified water and ammonia as polar molecules because they have big electronegativity differences greater than 0.4, were asymmetrical, and have unequal charge distribution. We also classified hydrogen fluoride as polar because it has a big electronegativity difference and unequal charge distribution.